Hi everyone, welcome back to Radical Chemistry. On this channel, I give lectures for 11th and 12th chemistry topics. If you are preparing for NEET or JEE mains, these lectures are going to be very useful for you. If you are new to this channel, please take a moment to subscribe so that you watch all my latest videos. Okay, in the previous video, we have discussed the resonance. We have learned what is a resonance hybrid, and what is a resonating structure. Okay, we have also learned the types of conjugation in the last video, and we have also studied the relation between number of conjugating positions with the number of resonating structures. The number of conjugating positions in a molecule are always equal to the number of resonating structures. Fine, but there is a point which I want to mention. I have missed in the previous video. A molecule is undergoing resonance by delocalization of electrons. But why does the molecule undergo resonance? What is the need for a molecule to undergo resonance? What is the need? The reason behind is the resonance is decreasing the energy level of a molecule. By delocalization, the energy is getting reduced. When the energy is reduced, the stability of a molecule will increase. The stability of a molecule will get increased. Okay, to understand it more efficiently, I'll explain it with an example. Let's take a molecule which has a 5 carbon chain. 1, 2, 3, 4. Now this molecule has a 5 carbon chain. Okay, it is a saturated compound. It does not have any conjugation. That means it does not exhibit resonance. Okay, and we'll take one more molecule which has a conjugation. This is also a 5 carbon chain. Okay, but this molecule has a conjugation and this molecule is exhibiting resonance. Now the energy level between this molecule is different. We'll number this 1, 2. The energy level of second molecule will be much lower to the first molecule. That is because of the delocalization. The delocalization is decreasing the energy, which in turn increases the stability of a molecule. Now the second molecule is more stable than the first molecule. Okay, understood? When a molecule has a conjugation, it will exhibit resonance to decrease the energy to become more stable. Okay, now I think this reason has given more sense to the topic resonance. Coming to our main topic today, we are going to write resonating structures for different molecules and understand their stability so that we can arrange the resonating structures in the order of their stability. By writing the resonating structures for many examples, we will be able to understand this. Before that, I want to mention one point. Number of resonating structures is directly proportional to the stability. Okay, more the number of resonating structures, higher will be the stability of that molecule. Fine, now we'll start writing the resonating structures for different molecules. We'll start with a molecule which has a pi and a pi bond in conjugation. Okay, first example is, okay, this is our first example, propanaldehyde. Okay, now we have to write the resonating structure for this. Now this pi bond and this pi bond are in conjugation. We have to know how the electrons are moving, the flow of electrons. When you see here, it is a carbon atom and here you have an oxygen atom. Oxygen is a more electronegative atom than carbon atom. We know that. So obviously more electronegative atom will attract the electrons. Okay. So these two pi electrons are attracted towards the oxygen atom. Okay, fine. So obviously these pi electrons will shift towards this bond. Yes, right? So the second resonating structure would be, this is the first resonating structure, and the second would be CH2. Now the pi electrons have moved from here, so there won't be any pi bond at this position. Now the new pi bond is formed between second carbon and the first carbon. Yes, and the oxygen is gaining the negative charge because it has attracted the 2 pi electrons, and now carbon atom is gaining the positive charge. Right, so this is the first resonating structure and this is the second resonating structure. Can you write any third resonating structure? Okay, let's write and see whether we can write the third resonating structure or not. If the electrons are shifting towards this bond, so there will be a pi bond here, so CH2 double bond CH. So this carbon will gain a positive charge and this oxygen has a negative charge on it. So this positive and negative will form a double bond here. So first and the third resonating structure are same. So this is not a new third resonating structure. This is similar to the first resonating structure. Okay. And also you see the number of conjugate positions here. You have only two conjugate positions. This is 1 and this is 2. So there will be only two resonating structure. And coming to their stability here, what do you think, which resonating structure would form a more stable one? If you are predicting that the second resonating structure would be stable, then you are absolutely wrong. The first resonating structure is more stable than second one. Okay, I'll give you a reason. When you see the first resonating structure, you see every atom has formed the maximum number of bonds it can form. Oxygen has formed 2 bonds, and here the carbon atom has formed 4 bonds. So every atom in this structure has formed the maximum number of bonds. And coming to this structure, the oxygen is forming only 1 bond, and here the carbon atom is forming 3 bonds. So the maximum number of bonds has been formed by this first resonating structure. So this will have the more stability. Resonating structure 1 is more stable than the resonating structure 2. Okay. So the rule number 1 is, for the stability, maximum number of bonds will have greater stability. When a molecule is following the octet rule, then it will obviously form the maximum number of bonds. So the maximum number of bonds are following the octet rule is the primary rule for stability. Whenever a resonating structure is forming the maximum number of bonds, that will gain the greater stability, and the remaining resonating structures would have lesser stability. Okay. So remember rule number 1. We are going to discuss 3 more rules. While writing resonating structures for other examples, we will be discovering the other 3 rules. Okay, we'll do second example. Now, here also oxygen. Now, you need to know the flow of electrons in this molecule, and also the number of conjugate positions in this molecule, in this particular molecule are. Here you have lone pair of electrons. So this comes the first resonating position, and this is the second, third, fourth. So four conjugate positions. So there will be 4 resonating structures for this particular molecule. You consider this one as the first resonating structure. So when you are writing the second resonating structure, the flow of electrons, what do you think? Will the oxygen donate the electrons or will it withdraw the electrons? Here the oxygen has withdrawn the electrons, but the nature of oxygen here is something different. You see, the oxygen is bonded to carbon chain with a single bond. The oxygen is bonded to the carbon chain with a single bond. And in this particular example, the oxygen is bonded to carbon chain with a double bond. When an oxygen is forming the double bond, when it is having a pi bond, the electron negativity of oxygen will increase. The electron negativity will be more. So when the oxygen is forming a double bond, it will withdraw the electrons. But coming to this particular molecule, it has only single bond. So in this case, the oxygen atom would donate the electrons. It will donate the electrons to the system. Now oxygen has donated the electrons toward the system, so it will gain a positive charge here. Yes. Okay. Understood? These pi electrons are shifting towards the ortho position, forming a negative charge. And these 2 pi bonds are same. Okay, this is the second resonating structure. And the third resonating structure would be, now this negative charge would shift sideways, and this particular pi bond will shift towards the para position. Okay, this has shifted towards the para position. This is the new pi bond which has been formed due to resonance. Okay, oxygen is still positively charged. Okay, when you are writing the next resonating structure, this would be third. These electrons will shift towards this bond, and this pi bond is shifting towards the ortho position. Now this ortho position has gained a negative charge, and these are the new pi bonds. Okay, fine. Oxygen is having a positive charge here. This is the fourth resonating structure. Okay. After coming to this stage, this negative charge will be moved towards this bond, and the electrons of oxygen atom which has formed a pi bond are taken away by the oxygen atom. Now this is the structure you are getting. Now this structure is similar to the first one. So you have obtained the four resonating structures, and the resonating hybrid would be the movement of electrons are from oxygen, and in the molecule, in the entire ring also, the electrons have moved. The electrons have delocalized. So the partial negative charge will be on the ortho positions and the para position. Oxygen is gaining the partial positive character. You can see there is no effect of resonance on meta position. Okay. Now out of these four resonating structures, you have to order them according to their stability. Okay. So we have studied the rule number 1 here. Maximum number of bonds will get the greater stability. All the four structures have the maximum number of bonds. This molecule has 3 pi bonds. So fine. And this molecule has 3 pi bonds. Okay. This molecule also having a 3 pi bonds, and this also has a 3 pi bonds. So all the resonating structures have the same number of bonds. Then how do you write the order of stability? Here comes the rule number 2. The rule is neutral molecules are more stable than the charged species, charged or dipolar. So neutral species are more stable than charged or dipolar species. So in this particular example, out of these four resonating structures, which is the neutral resonating structure? First resonating structure is neutral. So greater stability will be in the first resonating structure, and comparing the other three resonating structures. Now all the three resonating structures here are dipolar in nature. They have a positive charge and a negative charge. So how do you differentiate between their stability? How do you know their order of stability? Here comes our third rule, which defines the order of stability. Okay, what is the third rule? Unlike species, that means the positive charge and the negative charge have to be close to each other. Unlike species, closer to each other. And like species, that means positive and positive or negative and negative, they have to be far from each other. They have to be far from each other. So what do you understand by this rule? When a resonating structure has a dipolar nature, the unlike charges has to be closer to each other. Then the structure would be more stable. When the unlike charges are very far from each other, that structure would be less stable. Okay. So what do you consider here? You have to consider the charges and their distance between the charges, the positive and the negative charge. So when you see the second resonating structure, you see the distance. You can see only one atom between the positive charged atom and a negative charged atom. Okay, here you have one atom which is separating the charges. And coming to the third resonating structure, this is the positive charge, negative charge. Count the number of atoms which are in between. This is the first. This is the first atom, second and third. There are three number of atoms which are separating the positively charged atom and the negatively charged atom. So you can say second resonating structure is more stable than the third. But before that, we'll also see the fourth resonating structure, the stability of fourth resonating. Maybe the fourth resonating structure is more stable than second one. So we have to see the all resonating structure before getting into the order. Okay, we'll see the fourth one. Here, the positive charge and the negative charge atoms are separated by one atom. Only difference between the second and fourth resonating structure is it has occupied one left ortho position and it has occupied the right ortho position. That's the only difference. Both the resonating structures have negative charge on the ortho position and the positive charge on oxygen atom. So they will be having the equal energy. So equal energy means equal stability. Yes, so 2 and 4 will have the equal stability. And we have also compared the second and third resonating structure, which confirmed that third resonating structure is less stable than the second one. So obviously it will be less stable than the fourth one also. So third resonating structure is less stable than all the other three resonating structures. So this is the order of resonating structures. So by writing the resonating structures for these two examples, we have learned three rules of stability. So these three rules will help us to order the resonating structures according to their stability. Okay, so these are the three rules. We will also study one more rule. Okay, coming to the next category. Okay, yesterday we have learned the resonance structure and the resonance hybrid. Okay, I feel this practice session is helping you to enhance the knowledge of resonance. Coming to the examples of this category. Okay, this is our molecule. Now we have to write the resonating structure. But before that, what do you think about the number of resonating structures we will get? So to get the number of resonating structures, you need to know the number of conjugating positions. We have 1, 2, and 3 positive charges involved in the delocalization. So it is in the resonance. So there are 3 conjugate positions. That means we will be getting 3 resonating structures. Fine. We consider this as a first resonating structure. And the second resonating structure would be to form the second resonating structure. This particular pi bond is moving towards this side. Okay. Now there is a new pi bond here. Yes. And there is a previous pi bond. Now the electrons are moved from this particular area. So the electron deficiency will be on this particular carbon. So we are going to write the positive charge on this. This is our second resonating structure. And coming to the third resonating structure, these pi electrons are shifting towards this bond. So in this third resonating structure, this particular carbon is gaining the positive charge, and this is the new pi bond formed, and this is the other pi bond. So these are the three resonating structures, and the resonance hybrid would be. So what are the carbon atoms which are involving in resonance? 1, 2, 3, 4, 5. Yes, these 5 carbon atoms are involving in resonance. This carbon is not involving in resonance. So how do we write? You have to denote it with the dots until till this carbon. Okay, you should not draw a circle, that because that will give the assumption that the 6th carbon is also in the resonance, but that is not the case. Only the 5 carbon atoms are involving in the resonance. So you write the dotted line, and what are the atoms which are giving the positive charge? Suppose this is the carbon 1. 1, 2, 3, 4, 5. So 1, 3 and 5 carbon atoms are giving the positive charge. Delta positive, and this is delta positive. So this is the resonance hybrid. Now coming to their order of stability. Whichever the resonating structure is forming the maximum number of bonds, that structure is going to be more stable. When you see this structure has formed 2 pi bonds and a positive charge. This also has 2 pi bonds and a positive charge. And this structure is also having 2 pi bonds and a positive charge. So by following the first rule, we are not able to write the order of stability. We are going to apply the second rule. What is the second rule? That the neutral species are more stable than charged or dipolar species. You can see all the 3 resonating structures are charged one. So we can't apply the second rule. And the third rule, what is the third rule? That the like charges should be far from each other and the unlike charges should be closer to each other. But as you can see in the resonating structures, there is only one charge in the molecule. So you can't even apply the third rule. Then comes the fourth rule. Where the fourth rule says negative charge on electron negative atom. Okay, fine. And positive charge on electropositive atom are stable. So the fourth rule is saying that if the resonating structure have charges, the negative charge should be on the electronegative atom and the positive charge should be on the electropositive atom. Then that particular structure would be more stable than the other one. So we'll apply this thing to the above example. As you can see in all these resonating structures, the positive charge is on carbon atom only. the atom which is bearing the positive charge in all the three resonating structures is same. So we can't apply the fourth rule as well. So what is the conclusion here? How do you write the order of stability? So the stability of these three resonating structures are equal. The three have the same stability. They have the same stability and the same energy. Yes? Understood? So these are the four rules you need to apply to get the order of stability. Even after applying these rules, you did not find any difference between the resonating structures, then that particular resonating structures would have same stability and same energy. Okay, fine. We'll do one more example, and the order of this rule and the order of these particular rules is also important. First, you have to apply the first rule. If that is not helping us, then you have to apply the second rule. Then you come to the third rule. Then comes the fourth rule. So you can't jumble these rules. Fine. I hope these rules have given a clear picture of stability and resonating structures. Okay, we'll do one more example in this category where a positive charge is in conjugation with the pi bond. So what are the conjugation? What are the number of conjugating positions here? Positive charge is the 1, 2, 3, 4. So there are four conjugating positions. So the number of resonating structures would be 4. And what is the flow of electrons here? Here the carbon atom is electron deficient, so it will attract the electrons. It will pull the electrons from the system. Movement of electron will be towards this atom, towards this bond. So the second resonating structure will be something like this. Now this bond has moved, so you get a double bond here, and this particular carbon is gaining the positive charge by giving away the electrons, and this is the pi bond. Now to stabilize this particular carbon atom, these electrons are moving towards this bond. Now this carbon is stabilized by forming a new pi bond. Para carbon atom is gaining the positive charge. This is the old pi bond. Okay. Now to stabilize this para carbon, these electrons are moving towards bond. Fine. Now this ortho position is gaining the positive charge here. This is the pi bonds. These are the pi bonds formed. Fine. Now to stabilize this carbocation, these electrons are shifted towards this bond. So by doing that, you will get the first resonating structure. This is the first resonating structure. Yes, now the positive charge is on the CH2 group. These are the new 3 pi bonds, and the resonance hybrid would be the electrons are getting delocalized in the benzene molecule, and it is also delocalizing with this CH2 group. What are the atoms which are gaining the positive charge? Ortho positions and para positions. So they will gain a delta positive character. When a nucleophile attacks, it will attack the ortho position or para position or even the benzyl carbon over here, but it cannot attack the meta position. Fine. Now we'll write the order of stability. Yes, we'll write the order here. What is the rule number 1? Maximum number of bonds. Yes, in this you can see 3 number of bonds, 3 number of pi bonds. In this particular structure, 3 number of pi bonds, 3 number of pi bonds, and 3 number of pi bonds. So all have same number of bonds, so then you can't decide their order of stability by first rule. We'll go to the second rule where the neutral species are more stable than the charged or dipolar species. But all the four resonating structures are charged here, so you can't even apply the second rule. We'll go to the third rule where unlike charges should be closer to each other, like charges should be far from each other. But you can see only one charge here, so we can't apply the third rule. We'll go to the fourth rule. What is the fourth rule? Negative charge on electron negative atom, positive charge on electron positive atom is giving the stability to that particular resonating structure. But in all these four resonating structures, the positive charge is on only carbon atom. So you can't even differentiate resonating structures by this fourth rule. So the energy of all these resonating structures are same. The energies are same. So the stability will also be same. The stability of all these four resonating structures are same. So we have done two examples in this category. We'll continue with the examples regarding stability in our next video. Comment down if you have any doubts regarding this particular video, and also like this video because that will motivate me to do more such videos. Share it with your friends and also make sure you subscribe to this channel for latest videos. Thanks for watching.